All right. Thanks everyone for tuning in. This is a presentation similar to one I did probably 5 or 6 years ago. Um, but essentially, the sort of playing field's changed a little bit. And so, uh, what I'm mainly going to talk about is how we use CNC routers and the CNC router that we have at our workshop to help and aid our competitiveness as a team, Team 4613, the Barker Redbacks. And also more generally, how CNC routers could be something that your team could start using or your team could obtain if you don't have one already. And really looking at some of the positives and negatives of the various manufacturing processes. So to first up, you'll see this photo here. I'm not going to run the video because I don't think it's going to play very well. Just the classic sort of Barker Redbacks review video. But this is a pretty good frame here because you can sort of see what we're talking about. So this robot here, it's completely made on a CNC router. We've got these parts here, which are 3D printed. And there's plenty of other COTS parts, bearings, and a few other parts, motors, gears, which have been purchased, like wheels as well, have been purchased off the shelf. But pretty much all the metal machine components in the robot were made, designed by our students, and then made on our CNC router in-house by our mentors. So the entire bottom of the robot, I'm not sure if this is our robot from last year, actually, 2014, is one single piece of aluminium. And that's sort of an idea that I came up with in 2013 when we were wanting to make a really small robot chassis. Sorry, 2023, when we were wanting to make a really small robot chassis and really simplify the manufacturing and work out how best to leverage the technology and resources that we have as a team. Um, and this has been, I guess, just looking at it, has been the cause of some sort of like debate on like the Chief Delphi forum. But for us, it works really well because the cost of the actual aluminium to make the robot and to make this frame is only a few $100s. And you compare it now with the price of having a full piece of aluminium for the bottom of the robot for the belly pan, for 4 tubes, and then for any other ancillary gussets, nuts and bolts, and a whole range of other things that you would need. And so for us, we've got the ability to produce parts on the CNC router from large pieces of aluminium, and we want to leverage that to be most effective. Other parts you can see on here are these plates for the robot as well. Even the plates for the swerve drive, they're all stuff that we've produced and machined in-house. And really having access to a CNC router in our workshop really gives us that capability. Um, and I'll just continue on through the presentation, but I really wanted to say, and it's in the first, yes, this is what we saw. Um, what we saw in the video, what we saw in that photo is a robot that was nearly 100% made from parts machined in-house on a CNC router. We've got a pretty decent industrial CNC router, but it was something which was imported from China. It wasn't, particularly expensive, pretty in line with what you would pay for a base level multicam machine or something like that. And in our team, I'll just be completely upfront. Our students do design 100% of the robot parts, but we do have mentor help, which helps run the CNC router. And so the reason for that is mainly due to safety requirements, because it's a pretty high risk machine. It's an industrial grade machine that we use. And the other thing to think about as well is we've got plenty of students who would love to jump on board and use the CNC router, but those top students are also the ones which could be working on CAD of the robot, which could be assembling components, which could be doing driver practice if in the drive team. So it's really hard to find a balance between student and mentor in terms of that manufacturing aspect, especially when we've got at the school, we've got WHS protocols, sort of pushing to have that risk taken directly away from the student body. Um, and so we didn't see the robot driving around, but you all have seen us at the competitions, and a big reason for our performance and effectiveness and competitiveness as a team is because we can iterate mechanisms quickly for maximum effectiveness and efficiency. So um, we we prototype very rapidly. We make lots of polycarbonate prototypes and we use cordless drills to run them all. And we'll make several versions of a mechanism on the robot. Um, and that is what enables us to have a robot which actually functions well, and doesn't have issues and is also reliable because we can find the kinks in something, we can test it at our workshop. We can solve the problems and we can make those parts again. And that's not something that's possible if you're having parts made externally. If you're reliant on companies to produce parts for you, you're very much stuck, right? Because you'll design the parts, um, you'll send them off. It might take a week to have them produced, and that ends up being a very long turnaround. If you spend 2 or 3 weeks or 3 weeks designing a robot during build season and you send the parts off and then it takes a week or 1.5 weeks to get those parts back and then you assemble the robot and then you find out that the mechanism doesn't work or there's a part of the robot which doesn't work. You really don't have much time to fix the problems that you've got and really sort out those kinks before the competition, especially when you think about the fact that for us we go to competitions typically which are a bit earlier in the season, and so that means we need to work fast. We need to have time for driver practice. We need to have time for programming. So it's pretty tricky. So I'll just run through some parts that we make on our CNC router. And this is all recent. This is from an FTC robot this year. And so just to point out a few parts, this is a turreted shooter. And we've got these steel flywheels here. The steel flywheels were machined on our CNC router. We've got these aluminium parts. We've got this gear, and that was machined with a really small end mill as well. Um, and so you can see the robot is a combination now of CNC routed aluminium and a lot of 3D printed components. And that's sort of what has become a lot of our design. Like probably before we started buying a lot of before we had Bamboo Lab 3D printers and we would do like a lot of lathe. We would do a lot of like turning of plastic and various shafts and stuff like that for standoffs. But now it's become a lot more of combining aluminium and sort of 3D printed components together. So next slide, here we've got another example of a part, and this is the gear, the turret gear that was made for FTC. You can see we've got lots of really small holes here, which were drilled probably with like a 2 mm drill bit. And we've got this gear here. And something which you might have seen, we've made quite a few robots with like turrets or sort of gears and arms in the last couple of years. And so all that gear, all those gears are made on our CNC router. And so in this case, this would have been like a 1/8 end mill, which is a bit over 3 mm. And so that tool can go all the way down into the root of that gear and really create a pretty accurate involute gear profile. And all the parts that you would have seen as well, they're all pocketed down as well, which reduces the weight and enables us to maximize the strength of the part. And that's not something that you can do with like a laser cutter or a water jet cutter. You really can't maximize the strength of a part like a CNC machine can when it can leave like literally 1 mm at the bottom of the part. And the other thing that we can do is we can do chamfering as well. It's, a bit of a visual thing as well, but it is an easy way to prevent the parts from being sharp. Um, Next photo. Yeah, this is a steel flywheel that was made. So we broached this. Maybe it was actually done with the CNC machine. I think one of this was done fairly recently. But this is just a really simple, like cheap tool maker's vise. They're like $100, and we've just got this clamped onto our CNC router. And this is actually clamped onto the same fixture that we just used for our tubes. So pretty simple, but it shows you what a CNC router can do when it's used effectively, when you've got the right tools, when you've got the right feed and speed and the right strategies. You can really machine just about any material. And this was cut from some bar stock. The next, this is a pretty standard sort of plate part that we produce. And again, this is all made on the CNC router from some This would have been 75 aluminium plate. Hmm. All right, so just to go back to what I was going to say at the beginning, um, does my team need a CNC machine to do well? And I think it's really important that the answer is no, and it is not the answer. It is not true at all that you need a CNC machine to do well. You don't need to have access to a lot of resources to have expensive equipment. As an example, our robot in 2015 was entirely made with like really basic hand tools and like a really cheap drill press from Heron Forbes, which didn't really work very well, and like a drop saw just to cut the aluminium up. And that was a lot of just like trial and error and trying to get things precise to a degree. And that was our first year at the World Championship and that in St. Louis as well. And we came very close to getting to Einstein that year. We beat 148 and 1114, both of which had very impressive robots that year. And that was with a robot which was just built by hand. And the other thing is, it's even easier now than it was then because there are so many specific sort of off-the-shelf parts that you can buy before you could get like some gussets and stuff like that now, but now you can essentially get your entire chassis off the shelf, just supply some tubing to go with your swerve drive. The biggest problem for teams though is obviously the shipping and the time that it takes to get those parts from America. But if you are careful, you can use a jigsaw, you can use a hole saw, and you can make parts by hand. And you can even still do your CAD, and you can print paper templates, or if you've got a laser cutter or a 3D printer, you can make templates that you can then use to copy and get really accurate holes drilled. And then probably the biggest thing is that you might think, yeah, if you want to make a robot which does everything in the game really well to a really high standard, yeah, you probably do need a CNC machine to make that easier. But especially sort of in an Australian FRC context, building a simple robot that purposely doesn't do everything with a reliable electronic system, a reliable drivetrain, and finishing the robot early so you have plenty of driver practice and so you've got time to do software, that is probably far more important than having a CNC machine and then really trying to do too much with it and really that's probably a trap. That's even a trap I've fallen into the first time I mentored another team was had access to this equipment and then you try and build this really fancy robot and then the software team didn't actually have I didn't have the personal like mentoring expertise to do the programming. And so we sort of fell over there. And so probably the biggest thing is to work within your limits. Suddenly having the money to purchase a CNC machine isn't sort of a magic solution to problems that your team may have. But for us, it enables us to push our students' design a little bit further. And it means that we can have lots of students working on the computer, working on CAD. Whereas you can imagine it would be if you're trying to just like work on this small robot that you're sort of building as you go along, it would be difficult to have that many students involved. And so just going over why we would want to use a CNC machine for robotics, and this is for FTC and FRC as well. So a CNC router can machine parts with tight tolerances. All right, so this means you can have two parts, two drive rails, or two parts for an arm, and the bearings are going to align properly. And you can have proper gear center distances, and you can have proper belt center distances that you're not relying on sort of tensioners or having to use chain for various reasons. Um, and it enables you to produce complex geometries that hand tools really just can't match. And it helps to ensure your robot performs reliably on the field, right? Because you've got those tight tolerances. You don't have your bearings falling out. You don't have your gears breaking because they're meshing together poorly. The other thing is the rapid iteration. And so in the intense build season, speed is everything. I still remember where, metal as well, when you had 6 weeks and the robot had to be suffocated in a bag. Um, but a CNC router can turn a CAD design into a physical parts in minutes. Realistically, it's more like, an hour or two. But when you compare that with how long it would take to get those parts outsourced or to be relying on parts to come from America, you can understand that is a really big benefit. Um, and it allows teams and it has allowed us the ability to test, break, redesign, and replace the mechanisms faster than ever before, right? So we can do multiple prototypes in one day. The game can be released, and then on Monday the kids can be broken up into sub teams, and they can be on the computer, and then we can be in the evening we can be cutting out polycarb and working out what size wheels are going to be used, and we can have the kids there holding the two cordless drills and running the intake. And that's what gives us that capability, having the CNC router. And so I guess another question is, and this is a poignant one, because quite a lot of t FRC teams in America, you might have heard of these like services like Send Cut Sand or FabWorks or different websites which will do sort of metal laser cutting and stuff like that online. But for us, on-site production is really critical for high performance robot development. You can get sponsors on board to help you machine parts, but what often happens is the sponsors will put your work and your jobs to the side and focus on it when they have spare time because they're not going to be making money on it. So that can lead to delays. The other thing is a lot of companies which you might outsource to will be based in China. They might be really cheap, but because you've got Chinese New Year falling within the FRC season, it makes working with these manufacturers difficult. Because for a week before and a week after, there's sort of all these manufacturing delays and shipping and everything like that. The other thing, if you're looking to get paid manufacturing work, the setup costs for CNC milling of sort of the equivalent style parts would be really outrageously expensive. I think once I put my like the chassis into like Xometry on one of those online websites. And I think, for what costs us maybe $300-400 in aluminium was going to cost like $10,000 to get that part machined, even though it only takes us like about 6-7 hours to produce. You've got delays and excuses from suppliers, that mainly it's just the ability to rapidly iterate and do those multiple prototypes. But then also being able to expose your students and mentors as well, right? Because they have the opportunity to use the machine and that can uh, open up other employment opportunities for them. It provides the students and mentors exposure to real industry manufacturing processes. And also, really importantly, the students are involved in producing the parts in-house. So there's a really quick back and forth when the students are learning about design for manufacturer. So it's a good way for students to understand what can and can't be produced easily. So yeah, what can I make using a CNC router? I think I might just go fairly quickly through this, but yeah, all your flat aluminium, all your sheet stock, your tubing can be produced as well. Polycarb, that's a really good example of something which is good to produce on a CNC router. It doesn't laser cut that well, with like a normal laser cutter like schools have. And that's a really good material for making intakes and various things which get hit by the robots. But as I showed earlier with those gears and that flywheel made out of steel, like you can literally use the machine to make anything that you would need. We've even made like bevel gears for a swerve before. We haven't used them, but we've made them all on like a CNC router. Um, so yeah, specific parts, gussets, belly pans, intake plates. Um, it's it is very useful. A lot of teams will have a machine which is a bit on the smaller side, in which case you can do things like belly pans in two pieces, or you can just design your robot accordingly. And having the sensor router having the ability to manufacture parts from all these different materials is very valuable. And it's something that there's no real other machine on the market which suits, well, in my opinion anyway, which suits FRC as well, especially in terms of the space, the cost, the size of the machine. There's nothing which is really as effective for an FRC team to have. So just to compare how a CNC router is to other machines, you might have seen sort of CNC machining centers before, which have like which are in a full enclosure. They're quite restricted in the sizes of material that they can produce parts from. So the advantage of a CNC router, which is almost like a flatbed milling machine, is that the spindle spins really fast. So that means that you can use a small tool and you can actually slot through material. So typically with those big machining centers you might have seen on YouTube, um, if you were to make an FRC sized part, maybe this part for an arm or something like that, they would be cutting a large rectangular piece of aluminium plate out, and then they'd be putting it in a vise, and then they'd be machining pretty much all of it away to leave that part. And so in FRC, not many of the parts are rectangular or square, especially if you don't design for that purpose. And so there's lots of waste. And so a CNC router means that you can have our machine is actually a third sheet, so it's has a work area which is 800 millimeters by 1200 millimeters. So we get all our aluminium cut into three pieces by the supplier, and that means that the sheets are easier to move around. And so for us, we could almost fit an entire robot's worth of if of say 10 millimeter thick aluminium on one of those pieces. So we just put it on the machine. We have our program which runs, and we machine it all out. And the fact that the parts can be really close together, like if you're using a 4 or 6 millimeter router bit, the parts can be like 7, 8 millimeters apart, and there's really not much waste. Um, and you can nest the parts into each other. And so this reduces the cost of material significantly. So just comparing it with some other machines, I used to think, oh, a water jet cutter is the ultimate machine to have. You might know Team 359, the Hawaiian kids have one. Um, but they're very expensive to purchase. They're very costly to run. They're really noisy. They use like a huge amount of electricity, and they're actually very slow as well. So the same part would take quite a lot longer to cut out on a water jet cutter than it would take to produce it on a CNC router. The advantage of the water jet cutter is really for steel and other materials. And the other thing is with a water jet cutter, sorry, you end up with parts with a taper on them. And so then we can compare it to like a standard sort of CO2 laser like you might have at school. There's no doubt about it. CO2 laser cutters are really, really good for prototyping. They're a really good thing for a team to have access to. They're great at cutting plastic and sort of laser style plywood. They're very quick to use, so they're perfect for prototyping. But they do struggle with cutting polycarbonate properly, and they cannot cut aluminium at all. Um, and then another option, these are sort of going out of fashion a little bit, but the CNC plasma cutter, again, they can only cut conductive materials. You're not going to be able to do any prototyping out of plastic, and the poor cut quality and the tolerances are poor as well. So probably the best alternative for a CNC router would be a CNC fiber laser. And the high power fiber lasers can cut aluminium really well. So yeah, absolutely. If you've got access to one of these machines through a sponsor, through university, this would be a fantastic tool to use. They're very fast, they're efficient, but they can only cut 2D shapes. And so you just have to design with that in mind. We originally, probably like up to 3 years ago, we were designing our robot almost like it's 2D. Like you could produce all the parts on a laser cutter, but now we're trying to make use of the fact that we're using a CNC router more and only cut, 3/4 of the way through the material, leave that skin on the bottom, which really adds a lot of strength for very little weight. Um, yeah, so with those fiber lasers as well, lower power machines really struggle with cutting thicker aluminium. You need probably for an FRC use, probably 2 to 3 kilowatts. And then, yeah, you need a particular laser source and sort of head assembly, because otherwise you get a lot of reflection from the aluminium. And then sort of comparing it, it's a bit of a weird comparison, but comparing it to a normal FDM 3D printer, Bamboo Lab. 3D printing is great for prototypes and low load parts. They're really good and they get plenty of use in our team, especially with how easy and accessible they are for the students. And probably the limited strength and the size of part are the main weaknesses, as well as print time. You can imagine how long it would take to print out an entire robot's worth of parts. So what should I look like? What should I look for in a CNC router? So if you're a school team, you really need a machine or a university team, you really need a machine that meets all the relative and relevant safety standards. And so I've done a fair bit of research into this, and I've sort of provided guidance to a couple of schools and FRC teams on the matter. And so the best machine on the market for schools really is like the Multicam SM1212. It was called the M1212 up to sort of a couple of years ago. And so that's a half sheet machine, but the way that the machine is designed is it's very small, so it can fit through a double door. These are about 40K new. It's a lot of money with a manual change spindle, but they are made in Australia and have pretty good service and support, which for a school or other organization is important. And they have the required guards and sort of emergency stop switches to keep schools happy. And you might look at this number and go, that's a huge amount of money. How would my school ever be able to afford that? But this is the type of thing that takes a sort of a multi-year approach. So you'd be having to say a flag with the school. Like for when we at the school and we bought the first CNC router, I think that took like 4 years to get approved. Um, so essentially what the design and technology department did when they bought the machine back in sort of 2013 was they showed the benefit that the machine could have for all these different departments. So now even like I cut all this stuff for like the drama set and the musical set on it, all these different relief things and all these various other jobs. And so for schools, really showing them how they can use the machine in other ways is valuable. And that's something a lot of schools will do. I know, for example, at Macquarie University, the engineering department use the CNC router as well, and it gets used for robotics. So that's a way to justify the budget and the time for it. And so, yeah, you do kind of just have to think outside the box to get it across the line. I'll give an example of Pimble's Ladies College. They actually bought one of these machines, which is mentioned down here, the Omeo X8, and that was just because out of requirement, not necessarily because that they didn't have the budget, and that was something affordable for them, um, and that got them through, and got them starting to make parts on a CNC machine. But it was very difficult to work with the school. They were very unhappy about the machine in terms of safety. And so that's one of the reasons they were able to actually get a proper machine, one of these multicam ones, is because they could show that they had the need for the machine and they were able to show that it would get used. And it also solved a WHS problem, getting the proper machine which met all the standards. And so, yeah, there are plenty of more affordable machines on the market. So if you're a community team, a community organization, and you're happy to do your due diligence and sort of introduce your own safety procedures and everything like that, then you can get machines for four, five, $6,000, which really do the job well. Especially for community teams as well. If you can, there's so many CNC routers on the secondhand market because so many people bought them during COVID, wanting to make like side hustles, things like that. But with these machines, if you want to cut aluminium effectively, you really need to have a machine which has sort of square linear rails and a proper spindle as well, that can be air cooled or water cooled. A lot of these cheap machines will have almost like a repurposed sort of Makita hand router or something like that. They don't really hold very good tolerances and they break quickly, those spindles, when you're cutting aluminium. Then ideally ball screws as well. And as I've said, yeah, usually they're not compliant with safety standards for schools. You can get some of these which have a compliant enclosure. There's one sold by this company, BG Precision, but they're quite expensive for what they are. It's about $20,000 or even more, $23,000. And it's essentially like a small CNC router inside a sort of a full enclosure. And the big thing with schools is it's going to be very hard to justify if you spent $20,000 on something. Why do you want to spend, 2 years later, do you want to spend all this money and buy another machine? And so my suggestion would probably be, if you need to prove it out, maybe work with a mentor. Maybe a mentor is happy to have a CNC machine in their garage or in their house. That happens with one of the teams, one of my family members' mentors. But then probably see if you can budget every year, put some money aside to buy something which is going to suit your team for 5, 10, 15, 20 years. Get a proper industrial machine rather than something that you're going to be stuck with and then find out that it's not really the best solution for you. Um, and so just to explain a little bit about our workflow as a team and how we use the CNC machine. I guess I talked about this earlier. So yeah, students finish designs for various mechanisms and they have a mentor check what they've designed. And the reason for that is just to reduce waste of material and time. So do a quick check, make sure bearing holes have been drawn the right size, make sure the gear distances are correct, and make sure the belt distances are correct. And then those students can then approach one of the mentors about having the parts CNC machined. Um, and what we do is we use SolidWorks as a team. We might, I guess, probably maybe in a year, we'll see if we want to move to something like Onshape. But essentially, what we do is we produce these SolidWorks assemblies, and then we export the SolidWorks parts. And these are taken as either a step file or a solid part file and open in Autodesk Fusion. And so we use Autodesk Fusion for all CAM or computer-aided manufacturing. And so this is where parts go from digital 3D models into G-code programs that the CNC machine can read. It's essentially like a whole list of coordinates that the machine sort of moves between. And that's very similar to the G-code that a 3D printer would use, for example. We have template files preset on Fusion with specific tools, feeds and speeds, the size of spoil board, and the origin location, which makes this process quick. And we have a few alumni and mentors who help to run the CNC router for us. Um, and yeah, the CNC router is a high risk piece of equipment, so our policy in most cases is that the mentor must be the one to run the machine. And as I said before, even if we did have students spend, the hours running a CNC machine, it would mean the time is being taken away from them that they could be using to design the robot. So it is quite like a difficult balance. Yeah, with most of our older students, they all want to spend the time doing CAD, or they want, or would rather be focusing on doing driver practice or like software or something like that. And so before I talk any more, I'm just going to talk about safety, because we love that. Um, so the biggest safety risk with a CNC router is going to be eye damage from swarf, pieces of metal, broken tools, and yeah, safety glasses are really, really important. And obviously, it's something we instill in the first robotics competition, first tech challenge, wearing them at the competitions. But especially when you're using one of these machines, it is really important. Things do break and they do fly around. Um, and we've got plastic panels around our machine, which sort of separates it off so that only the operator is really at risk of having something like that hit them. And it means that other people in the room aren't at risk of being hit by flying things. Because it's not just eyes, no one wants to get hit by flying stuff. And then also entanglement and pinch points. Our machine is very powerful. Plenty of other center routers are as well. Um, the machine is used to pushing the router bit through metal, so it won't realize it's crushing you. So we have a taped out safety zone and we stay away from the machine while it's operating. The other thing is no long, loose hair, clothing, ties that might get caught up. That's not good. Touching the end mill while it's spinning is really bad. Even while it's not spinning, it's still very sharp. So yeah, if you need to adjust something, you need to make sure you pause the machine and turn the spindle off. The other thing is noise, and this is something to think about if you're looking to get one of these machines as well. CNC router is noisy, and so we make everyone in the workshop wear earmuffs while it's working. And then a lot of safety also just comes down to proper training, safe lifting of material. And the last point, this is one, yeah, but it has made me sick before we came up with a better solution, is the oil mist. Cheap misting units that you might buy on eBay for $20. They essentially create this big fog which hangs around and you breathe it in and then you feel sick. So we use this Trico lubrication system, which is just putting out little bits of oil droplets mixed with air, which just goes straight onto the aluminium. And so then just a bit more about the basic tooling selection. I know quite a few of you have probably hearing information that you've heard many times before. But most CNC routers don't have an automatic tool changing spindle. We're quite lucky to have a machine with one. Um, but this means that it's quite time consuming to change the end mill sizes and drill bits. And so if you don't have an automatic tool change, then my sort of personal and professional recommendation is to standardize on 4 millimeter single flute end mills. Because a 4 millimeter end mill can drill and bore all the holes that you need for bolts, rivets, and screws. And it will even happily create, your special 4.2 mil holes for M5 threads if you like doing that. And it can also cut small features and pockets, and it's still pretty efficient. Once you go smaller than 4 mil, your cutting speeds and efficiency just really starts to drop off a lot. Even the move from 4 millimeter to 1/8 or 3 mil really drops it down a lot. If you think about it, the router bit is essentially just like a beam or like a bar. And so if the router bit is twice as wide, then it is 4 times the strength. All right. And so you can imagine you might think, oh, we're moving from a 4 millimeter end mill down to a 3 millimeter. It's actually more like half the strength. And so the amount of cutting force that the tool can withstand is less. And the smaller tools as well, they're just less, they're less durable against the parts coming loose or vibration. And so, yeah, it's really important that you only really use single flute end mills for your routing in aluminium and plastic. For plastic, you can use like a down cutter or something if you need, but especially for aluminium, um, two flute end mill, four flute end mill, all these different other end mills, they don't really work properly, and you'll just end up having very, very poor results, especially if you're trying to cut all the way through the material at once. And so the big reason for that is chip welding and recutting of the chips is what causes the tool to gum up, and then once aluminium is sort of gummed up onto the tool, things start going downhill very quickly. You get like all this welding, and it's just not good. Um, so a single flute provides a really big sort of, it's called a gullet is the term, where the chip can fit. Whereas a lot of smaller tools will only have a very small slither. And that's mainly because those tools are designed for cutting steel, where the spindle and the feed rate is sort of higher comparably, and you're supposed to be creating very thin chips. Um, it's when you're cutting slower and you're creating very thin chip. And so the single flute allows the aluminium or the plastic chips to escape easily. And the evacuation of the chip as it is flown away, as it is thrown away, prevents the hot aluminium chip from being re-welded onto the tool. Polycarb as well is really important that you're cutting fairly quickly. The same with like acrylic, Delrin, any material like that. If you're going too slowly, the plastic melts. But they are typically more forgiving than aluminium. So with aluminium, if you genuinely go too slow, and I've put some speeds down here, which would be like the maximum spindle speed you can go in, like 15 to 20 meters, 15 to 20, what's that? No, like 1.5 to 2 meters a minute. That is pretty much perfect. If you go much faster, you're putting a bit more wear on the tool, a bit more load on the tool. You can go up to about 3 meters a minute or 3,000 millimeters a minute. But if you go much slower than, say, 1,000 millimeters a minute, that's when you're going to start having those problems when you're actually cutting too slowly. And it's something that just takes a bit of time to realize because, and it's a little bit backwards from what you expect because you've got poor results on your CNC machine, the cut quality is poor, and so um, you'll think, oh, I've got to I've got to, you know, decrease the speed. It's not working very well. But it's actually the opposite. So you need to be cutting slightly faster if the cut quality is very poor because the heat is remaining in the material rather than being evacuated with the chip. And so, yeah, as I've said, especially for a team just making a few parts at once on a smaller machine, if you're doing a lot of parts at the same setup, if you're just doing one or two parts at a time, the programming of the job, the screwing down of the material is probably going to take about the same as how long it actually takes for the cutting on the CNC. So what's the rush? There's no need to stress over like a 10 or 15, 20% improvement, in my opinion. So then this is probably the most important thing, and this is work holding. So if you're familiar with like a laser cutter or something like that, the great thing about a laser cutter is that there's no force put onto the material. The laser just goes around and sort of cuts. But with a CNC router, the same. It's just like what Newton's third law. Oh, second, it pushing. You're pushing on the every force has an equal and opposite reaction. So the tool is pushing on the aluminium, and the aluminium is sort of wanting to move as well. Okay, so while the cutter is pushing the chips back, the material is going forward. And so if the material moves at all, the tool will typically break. And that's because the router bits, or at least all the ones you should be buying, don't buy any which aren't solid carbide. And it is a very hard, very stiff material, but it essentially has no ability to handle any sort of deformation. It will just go straight from being perfectly straight to being snapped. And so as soon as you've got any material moving, a lot of the time the cutting tool will just break and your part will get ruined as well. And so what we do, and this is what I've always done, and it works really, really well, is you have a spoil board on your machine. MDF works really, really well. Plywood doesn't work that well. You have your spoil board, and you have the spoil board bolted down to the machine. And so the idea of the spoil board is that it's a sacrificial layer. So as you're routing, you want to cut a little bit further down, um, and it also protects the machine against any accidents which you might have if you forget to set the height of a tool or if you make an error in your CAM program. So what you do is you bolt the spoil board down, and so we use like 25 mil, but I also would use 16 mil, was just a bit lighter. So you bolt that down to your machine using the T slots and nuts and screws yeah, and bolts, and then and that is then fixed. So that MDF is not going to move anywhere. You've got, four or six bolts holding it down. And then you put your sheet of aluminium on. And in each corner of that aluminium, you drill a little like 5 millimeter hole with a cordless drill. You can do it with a machine as well. I just do it by hand. And then you can put four screws in, and that will hold that material perfect until you've got the parts drilled themselves. And so then what you can do is you can pause the machine, turn the spindle off, and say in two or three of those holes that you've drilled in each part, you can add like a chipboard screw or a standard woodworking screw, and that is going to hold those parts really well. You can also use tabs in the aluminium to hold parts as well, and that is sort of like a personal preference. I personally quite like the screws because it's just like guarantees that the material is held down well. And what you can do is you can get a sharp woodworking chisel and a mallet, and you can essentially just go around and you put the edge of the chisel flush up against the part, and you just do one little quick hit with the mallet, and it will cut through the tab. Um, the biggest problem with the screws is, and I've done this, and I'm sure other people have done this many times. You, you put the screw in the wrong place, and then the router bit hits it, and then the router bit just gets broken, and it either snaps or it gets like chipped, and then it's just really, really annoying. But it's sort of a price that you have to pay. The other thing you can do, and I have done this quite a bit in the past as well, is you can actually go to Bunnings and you can buy brass screws. They're like fairly expensive. I think you end up being like 50 cents each, and they're really fragile because if you put them in with like a drill on too high of a torque setting, the head just snaps off. But if you're not confident with using the steel screws, you can use the brass screws. And if the router bit hits the screw, it doesn't cause any damage to the tool, because those tools can also machine brass happily as well as a non-ferrous metal. All right, so next slide. Um, oh, we got two of this one. Yes, so um, here's an example of the work holding that we use. This is a part that is in process here. You can see we've got the nice, 7075 aluminium here, but there's loads of screws. Screws here, screw, screw. So that's holding the part down and holding it nice and flat. And then I imagine some of these parts, once they're finished, would have screws in them as well, or be cut out with tabs as well. And so that's what we do. That works really well. As you can see here, though, CNC router is also messy, so you have to clean it. That's pretty standard. That's what you'd expect from any machine. It's especially messy when you machine all the material out. So something I'll add I haven't talked about is and this is something we used to do. Um, it's much quicker to cut the actual part out. So if we're cutting this pocket out, it's much quicker to just cut around the outside. But the problem is when you're cutting around the outside, the little bit inside then comes loose. And so most of the time that's okay, but sometimes it can get jammed and it will break the tool. But worse than that, it can get jammed and then fly somewhere really quickly. And I've had situations with my own like machines cutting aluminium where you might get a little piece flying across the entire room. And so that's why the reason that you see all this mess here is that now, as our policy, unless it's very specific, we will just machine all the material away because it's much, much safer. And it means that the machine can be run, the machine can run without needing to stress about whether the stuff's going to get caught and the tool is going to get broken. Um, so, questions? Happy to answer any questions you might have or talk a little bit more about how we use sort of the resources that we have. But yeah, I'm not sure if there were any questions in the chat that I didn't see. Um,
Yeah, we had a couple. I think you answered a few of them, which was
okay.
which machine you recommended. There was another question asking about the process. So why do you CAD in SolidWorks and then move to CAM in Fusion 360 instead of
Ah,
doing both in Fusion? Or sorry.
great. Fusion is not a great software for doing a big assembly. So I actually use I use it's weird at school. As I work at Barker, we use Fusion and we have used it for quite a while in like the TAS department when kids are designing like their woodwork project or they're designing like a chair or something like that. Oh, here I have seen the sorry, I've just seen the chat come down. But the biggest problem with Fusion is that yeah, the joints are a bit difficult to use. The mates in comparison with SolidWorks. Um, and essentially just the assembly like we've always just struggled to do the assemblies. It doesn't have the robustness to do the really complicated like full in-depth assemblies. That is a really good that is a really good question though. Yes, it would help a lot if we could use something like Fusion to do everything in. But at the end of the day, it's not a big uh, loss for us. And we are looking to probably potentially move to Onshape in the next couple of years. And I know they're going to have their own CAM package, so that's something that we might explore. But at the moment, yeah, using SolidWorks, especially as you can actually import the solid parts, like the native SolidWorks format into Autodesk Fusion. I don't know quite how that works, but it works. So for us, that's quite reasonable. Probably the biggest thing, though, the reason that it would be nice to have an all-in-one package, um, is you could make changes as necessary to the CAD parts and have it automatically update in Fusion. We can do that, but those modifications have to be made in Fusion. Um, do you think what was the next? There's quite a few
So
questions.
you've got another question, which is what training does the team have before designing for the CNC, which
Yeah,
I guess it's like, what are your design for manufacture
yeah,
principles?
sure. So that's really just practice. So we have students join us in year nine, um, and we essentially run the entire FTC program that we run here at Barker is essentially training for FRC. And so that's why for FTC, all the robots are always custom machined and have all these 3D printed parts because we push them to do that. We push the students to learn. And so I would say probably that the biggest training is that they've had that practice in FTC when they're doing a lot of 3D printing, and they use a lot more like polycarb and stuff like that which is a lot cheaper and easier to produce. And then we do workshops as well, mechanical design workshops run by their mentors, which the students will come along to in the off season. So we've been doing that pretty much like every afternoon or a couple of times a week since the middle of the year, really. And now the students have been doing FTC as well. So like the students go into the the FRC build season, having just come out of the FTC build season. Um, Perfect. What's the next question?
The next question is, we tend to cut parts in large batches to reduce the setup time, but this means the jobs take a long time to run. How do you decide if a part is worth CNCing versus hand manufacturing some in parallel to the
Yeah,
CNC?
good question. I can't really think of any example, like especially in the last couple of years, we probably. Oh, sorry, Mel. How are we going for time? Can we run like 10 minutes over, or do we have to finish it?
We don't have to finish bang on 8.
All right.
I'll go with
Yeah,
plus
you'll
or
give us
minus
another
10
five
minutes.
minutes.
That's
All right,
fine.
no worries. I would say if it's a part, we mainly just do a lot of things on the CNC machine. Like if it's something which is worth doing by hand, like that would probably be when we use the lathe, when we do turning of parts on there. That's probably the best example of like hand manufacturing. The other thing that we do probably manufacture is, or at least we used to, is like bumper brackets from angled aluminium where we drill those. Now we've gone to a little bit different of a solution, which again we use the CNC machine for. Um, and so probably for us, where the question says, oh, we cut parts in large batches to reduce setup time. We do that as well. But what we also do is we keep the CAD model of the sheet of aluminium where it's been cut, which means we can nest the future jobs because there's always little bits which are done wrong, and bits which break and things like that. So we keep the setup document so we can nest the pieces into the rest of the sheet and reduce the waste. But we mainly just CNC pretty much everything or just 3D print it or do it on the lathe, really. Um, would you say that
Um,
Onshape is a good idea for a rookie community FTC team? Oh, definitely. I think that would be a great choice. Because in the design department at Barker, we've just moved to well, at least for next year, we're moving to Onshape Education Enterprise, where we'll have our own like single sign-on domain. But yeah, there's so many resources for Onshape now. I think especially for FTC, it's probably even better for FTC than FRC because there's all those like libraries of all like the Go Builder and Rev parts and stuff in there. Um,
there's increasingly libraries at
yeah,
FRC
there's a
parts
lot of
available now.
stuff. Do you think a CNC router would be a worthwhile investment for our school with five or so teams? I would, if no other department would use it. I would think that you can get the other departments to use it. If you talk to the TAS department, um, I'm sure they've had instances where they've had like students who've done things for major works and where they would benefit from it. And so, yeah, really almost just like you have to do a bit of a proposal to get the budget over the line with schools. And the more benefit that they can see with it, and the more individual departments that can benefit, the better chance you've got someone who will be your hero, really, and try to get it over the line. Um, but yeah, absolutely. I think for five FTC teams, that would be a no-brainer to me. Um, I don't think the Unshaped package. I'm not sure about that. I'll have to have a look at the Unshaped cam about the school accounts thing. I'm not sure. Hopefully, it is available for us when we get the enterprise. You'd have to pay a little bit for that. All right. Are there any other questions?
Everyone feel free to post other questions in the chat. One from me then. When
Sure.
you are bringing sort of new manufacturing or mech mentors on board, how do you train them on the CNC?
Yeah, so that's a really good question. So pretty much all the mentors that we have are actually team alumni, and that's something which we've focused quite heavily on just for like continuation and like our ability to keep running the program the way that we want. And so a big part of that is offering those alumni the opportunities to like because we've got a group doing like Vex U, for example, Vex University. And so a big reason that the alumni and the mentors will learn how to use the CNC router is because they need to use it in order to make their parts of Vex U. And so probably the best way to teach someone encourage someone to learn is to intrinsically motivate them. And so that is the fact that they can't make their robot otherwise without using the CNC router because we don't, and the other mentors don't really want to help them use it because it's supposed to be them making the VexU robot. Um, but essentially, I normally and one of the other mentors that uses the machine will do like a workshop with the mentors, and then if they're really keen, then they will have a bit more like one-on-one training. It is the type of thing which does take a lot of time to learn. It's not something you can learn from a video. It's not something you can learn from just reading a document. It does need to be one-on-one with someone where you're really having a good grasp and you're being shown everything and you just sort of guide and mentor them as they're developing their confidence a little bit. And that's mainly because of the hazards of the machine, but also how easy it is to make something which isn't right and make things go backwards. So that's really like an iterative process. And like we'll have the mentors try cutting out some plywood and different things and some polycarbonate, whatever, until they get comfortable. But even then, we might have a mentor who's been using the machine for a couple of months and still need a bit of a hand from one of the more experienced mentors. What are your uses for CNC in the off season? Yeah, great question. FTC is the main use. We didn't really do any FRC off-season projects this year. It is hard to, it's just busy. Like the students are busy. But yeah, FTC is the main one. And FTC, yeah, the robots are almost like 50% 3D printed and then 50% aluminium CNC. So yeah, that's what we use it for. And then yeah, Vex, the mentors using it to do their own Vex University as well, which is good. Because that just really encourages them to learn. And then the other thing is that some of the other mentors will use the machine to do some of their university projects and things like that. So we had some of the students, I think last year, some of the mentors made like it was for at UNSW, their first year project, they had to make some submarine or something like some submarine ROV thing, and they had it made it all out of machine plastic. Um, what are some specific recommendations? Yeah, great question. It really depends. If you're a school, you actually are quite limited, especially if you want to do things by the book. You do have to put some serious money together and get one of those multicam SM1212s. I'll put my email down in the chat. You can send me an email and I will send you or answer your specific questions. Um, but yeah, if you're a school and you want to do everything properly, you're looking in that $20,000 plus range. If you're a community team and you can make it work, you can make use with like a machine like this. I'll put it in the chat as well. This was actually the first CNC router that I bought, and then that was when a lot of like not many FRC teams had them, and then it's grown a lot from then. Probably in the last 5 years or 6 years, there's a lot more FRC teams which have CNC machines now. Is there a need for prioritizing parts? Yeah, great question. About the prioritizing certain parts. Uh, um, we really just do what we can. Like, yeah, we try to be really upfront with the students about when they need to have their stuff designed. But as we know, things always happen and mistakes are always made and things to be made. Like, we really just try the best we can to have all the parts done. Normally, we would try and get students, the multiple teams to combine, like if everyone needs something made out of like 6 millimeter aluminium, we would try and combine as many of those jobs together as possible. Because obviously, FTC is smaller robots as well. There's less machining. Probably the biggest thing is the 3D printing. That's probably the biggest hurdle. Like we've got several of the Bamboo Labs 3D printers. I think maybe four or five of them. Like they're not super expensive. But they'll all be used, and the students will all be trying to like fight over it. And like the print will finish, and the kids are trying to take the part off the plate while it's still hot because everyone wants to get their next print job going. And so, um, probably that is yeah, just being like upfront and trying to get that good culture of people wanting to share is really good as well. Um, yeah, I would definitely say that CNC machine would help with small FTC teams, but if you've got one single FTC team, it might be a bit hard to justify. The great thing about FTC is the loads and impact is a lot less. You're not dealing with, 125-pound robots with, a 12-pound battery driving across the field, incredibly fast and hitting your robot. So like you can get away with 3D printing and for so many parts. And a lot of the other parts you could make by hand or just simple aluminium things that you could fabricate or you could, use an online service, like an online laser cutting service. There's a couple out there in Sydney now, and maybe spend, $300, $200, $300 on that. That might, if you're a single FTC team, that might make more sense. But then if you're a FTC team, which is, trying to be really competitive, and you'd quickly realize that like when you added up the price of all like the Go Builder extrusion and all these little bits that everyone uses, that gets really expensive for a robot anyway. That can be a couple of $1,000s just in those buying those extrusions which have all the holes and everything in. But yeah, look, of course it'd be a great help FTC teams. If you've got four members, I'd probably try and focus on 3D printing, or if you've got someone's got access to a school they're at with like a little CO2 laser, you could see if you can get some like Delrin sheets or something, or even some really good laser plywood. That might be okay. Yeah.
Plywood has
Sure.
fallen out of popularity in FTC recently, but back, looking sort of 10 years or more back, those robots were often laser cut plywood and
Yeah.
fantastic.
Yeah. Yeah. No, to have the Tetrix and the modern robotics. Oh, all the wires will come out. All right. But yeah, no, exactly. And so that's really the benefit for FTC is the forces are much lower. And so that's why you can get away with a lot of 3D printed parts, just PLA, Bamboo Lab PLA or eSun PLA, and with a couple of walls, and that's really strong enough. Um, yeah, so great question about the CNC. So CNC is really good for aluminium, and polycarbonate because those two materials you can't really cut on a laser cutter. You can cut thin polycarbonate, but it's just not good. Don't do that. Um, and then your 3D printing. So the CNC is really for 2D parts. As soon as you're starting to get thick blocks, like blocks of aluminium, it obviously starts getting expensive and it starts taking a long time to make. So that's definitely not something which is necessary for FTC. Um, and so, yeah, definitely, if you've got larger parts, joining pieces, hoods, shooter hoods, and all these different parts of the robot, you can definitely just make all of those 3D printed with PLA. And the great thing about the 3D printing is you can just print lots of spares. Um, Ideally, you don't want it to break in the match, but it's easy to replace and it's cheap. Um, Laser cutter, yeah, laser cutter is really good for plastic like Delrin or doing prototypes. if you've even got a CNC, if you've got a CNC router and you're doing FRC, having a laser cutter to make some cheap plastic or cheap wooden prototypes is really good. It's really fast to iterate on because it just cuts around the outline rather than having to use a CAM program like, Fusion to do that, which adds time. So yeah, I think a combination of a little bit of CNC aluminium and 3D printing can go really, really well in FTC. And if you were careful, you could probably get away with just using laser cut plastic for pretty much the entire robot. Probably the biggest place you would choose to use aluminium or plastic is in areas where you're going to suffer from weakness along the layer lines of the part. And that is something which you can sort of solve other ways. Like I've made plenty of different things where you put sort of threaded rods through it to try to take some of that stress off the layers. But yeah, really the best advantage of a CNC machine is cutting 2D material. Best advantage of a 3D printer is obviously making those 3D objects. And so there is quite a big difference. But for your 3D printer, you can print all your pulleys. That's fantastic. We've on one of the FTC robots, there's a load of like 3D printed gears this year, and it's really good that you can get away with that in FTC because the loads are lower. And that saves so much money being able to 3D print some gears out of PLA, 3D print some pulleys, and then just buying some belts from the local industrials like, RS Components or something is help do like a really, really cheap robot, comparably with having to source all these parts from, Go Builder or other suppliers. Um, yes. Yeah, we there's a lot of 3D toolpaths. Um, we what's an example? In 2023, we had that big arm where we had the carbon fiber tubing. And so that was all done with 3D toolpaths because the actual parts were machined with that curved clamp surface. And that's probably the best example that I can say. Otherwise, yeah, we have made some like a few bevel gears and things like that before, which again are 3D toolpaths. Most of the 3D stuff we've done has just been using like the 3D parallel toolpaths or um yeah. Um we actually use the 3D toolpath function in Fusion just to cut out our normal 2.5D toolpaths because rather than having to go and individually select each pocket, you can just select the part overall and it will identify the pockets really easily. Is there any more you want to add to that, Will? Or yeah, so mainly just for like making round stuff to be clamps on tubes, round tube. That's been really useful. And that's something the machine's quite happy doing as well.
I might ask one more question of my own, and then we might
Okay,
wrap up
sure.
the
I don't want
recording
to, I'm
and
conscious that
see
it's
if anyone
also
wants
your
to chat
evening.
afterwards.
So
My question was just that I assume that when you are going to set up your jobs, the mentors do some kind of review of the parts the students have generated.
yes,
Beyond
yes.
just a design review, but more like from is this a suitable for manufacture part? What are you looking for at that stage?
All right. So yeah, we will do the functional design review and we'll do that when the students have been working. Like we have a computer lab, and so students will be working on the desktop computers with the monitor and they'll finish designing their mechanism, for example, and they'll call the mentor over and they'll say, "Is this ready to produce?" And so we don't like wasting material. And the biggest thing is not even $100 of aluminium wasted. It's like the time to produce something and then to assemble. Because a lot of the time you'll produce something and start assembling it, and that only then it was when you realize that it's wrong. And so that what we do is we're looking the mentor will look through at the overall mechanism, and of course the student has discussed it with them before as well, But yeah, they're looking at all those main aspects which would make it not work. So bearing hold, tolerances, the mechanism overall weakness. They were looking at how the pocketing looks, if it looks like it's going to break. Um, if they're using gears, they'll be asking how do they calculate the sense distance, run me through those calculations. We use all those online sort of calculators on those websites. Um, and then the belts as well, explain the working on the belt, and then we'll just go through it and make sure there haven't been any errors. And then the other thing is, and this is really important, being in Australia when we can't just, order we can't just have things the next day. The parts that the students have designed with, we actually check that we have them. So the gears, do we have that gear? Do we have that wheel, that belt? Sometimes, and this is something which has happened quite a few times, a student has designed, we've got a lot of belts. We buy the belts in bulk from this sort of Chinese supplier, which means we can have a stock. But someone will design, that's right, that's right. Um, um, yeah, we've had problems before where things have been designed with things that don't like 112 tooth belt, 116 tooth belt, something which does exist, but not something which you can easily get, and then you end up having to find like a real interim solution. And so that's kind of like you take the cat out of the bag by allowing the students to design their mechanisms, all these different things and belts, but then they also need to keep in mind what we do have, especially if it's towards the like competition end of the season, when if it's going to take 10 days to get a part in, that's just too long. And there's a lot of cost. We try to avoid like ordering a lot of stuff like willy-nilly. We just try to do big orders at once to reduce the cost. So yeah, that's all the design review really, like just functionally. Usually we've already done, if it's like an intake or something, we've already done sort of testing. Um, and then if there's any other issues, we even try and like test things. This is a good one. I'll say this before we finish off. Like if we've got parts we're machining and a bearing has to fit in it or a tube has to fit in it, we will pause the CNC machine before it cuts the outside of the part. We will put the bearing in the hole. We will get the tube and we will try and shove the tube in the part while it's still on the bed of the machine. Um, we will test, yeah, if bushes fit and if when we've cut a hex, was we cut hex like thunder hex holes, we will get a piece of the shaft and we'll put it in and make sure it fits in. What else? Yeah, that's really it. So that is a lot of the checking which we do as well happens on the CNC machine as well. And was that can be tolerance issues as well. Like you can have problems with tools and program. But yeah, really just trying to prevent and reduce waste of material and waste of time. We do try to be as unwasteful as possible. Like we collect all our like aluminium swarf and offcuts up and we like take them to the scrapyard once a year. So yeah, we do try and reduce the waste because FRC is a very wasteful competition. Yeah. Any other questions, or we might just wrap up there? So
I
that
think we'll
sounds
wrap it up
great.
here. Fantastic. All right. Thanks very
No
much,
worries.
Alistair. It's been
My
a
email's in
fantastic
there.
visit.
Yeah, if they can send me an email if needed. No worries. They
Fantastic.
know where to find me.
Thanks very
Discord
much.
or
I'll
something.
end the recording here.
No worries. Thank you.